Hello, Astronomy 101 students. Welcome. Um, this is a standalone lecture that you are supposed to watch remotely within about a week. And it's called an overview of astronomy. So it's just a basic um, um, overview of all that astronomy classes deal with, Astronomy 101, even a little bit of Astronomy 102, so you have an idea of the broad perspective of astronomy encompasses. And this is being recorded here as a makeup class. We had our Tuesday, January 27th class canceled, still due to recovery from the snowstorm. And so this is a makeup by watching this standalone lecture here now that will take you about 45 minutes. You'll be prepared to do homework one. Homework one is due on Thursday, February 5th. So you should absolutely watch this before your homework one, also certainly before your test one. Yeah. All right, so here we go. Click over here. So what are the broad goals of our astronomy course? Certainly to achieve an appreciation about the scale, size, and structures of the cosmos, and we'll focus a lot on that in this first part of the semester. The semester is split into three parts. There are three general tests and one final cumulative test. So this first part is about this size, scale, structure of the universe, and understanding the motions of the universe as well. Understanding the nature of science, how astronomy is done. How astronomy is done is you're going to see sprinkled all throughout the semester. The nature of science, we'll talk about the birth of the scientific method by the second part of the semester, and how we first understood the motion of the planets. That you come to appreciate science and the use of critical thinking in your everyday life. Develop an interest in studying and being curious or reading current astronomy events as a lifelong learning activity. All right, I'm going to go over here things we may have said and retold in our lives. And I want you to pay attention to each one of the sentences and think about whether you've heard of that, whether you've even said that before. And then I'll highlight what's the reality behind it, and pay attention how you could have reached the same conclusions without taking an astronomy course, without needing to have any kind of special degree or anything. It's just by being observant of the universe, the world around you. So this is something you may have heard or even said, what goes up must come down. Well, haven't we sent rockets to other planets? We've sent satellites to the moon. The moon is not a planet, it's a satellite, but we sent things to the moon. We've sent there are satellites in orbit around the sun. How many probes we sent to Mars. So, depending on the energy and the speed we give to those rockets and those objects, they will eventually escape the gravitational energy and the gravitational pull of our planet and will not come back down. So up must goes up must come down, not true for everything, right? It depends on imparting enough energy to that object. So you don't need a degree for that. You can think about things you know already, and refute these type of argument, right? The sun is a yellow star. Well, Kids tend to paint sun as a yellow star, etc. But the sun actually emits all rays of light. Don't you see a rainbow of colors, right? When the sun is shining at a certain angle and there's rain clouds on one side of the sky, you sometimes will see a rainbow. What is a rainbow? All colors, right? So where are all these colors coming from? From the sun. And what happens when you put all the colors together? You get white. The sun is a white star. It's not yellow, it's a white. And if you've seen any picture of astronauts looking towards the sun, they will see a yellow star when you are above our atmosphere. Sorry, a white star. When you're above our atmosphere, it's white. And even during the day here, right, when the sun is high up in the sky, you see how it looks more whitish, right? And it's when it is lower in the sky that we have a tendency to think that it looks more yellowish, and depending on the day, if there's a lot of haze, etc., in the sky, we even say it looks orange or it looks red, right? So these colors are in effect a lot of our atmosphere, and we'll talk more about light going through our atmosphere throughout the course, okay? But the sun is actually a white star. White is the combination of all the colors together, and the sun is responsible for all these colors. The light produces all these colors, so the sun is white. Weightless astronauts left Earth's gravity. So think about it. To leave Earth's gravity, you need to go really, really far. What is orbiting around the Earth, bound to the Earth because of Earth's gravity? The moon. The moon is moving around the Earth, right? Why is the moon moving around the Earth? Because the moon, so far away, feels the Earth gravity. Astronauts, when they are in the International Space Station and all, they are only 300 miles above the ground, only 300 miles above the ground on the Earth. So they're really not far from the surface of our planet, and much, much closer than the moon is from our planet, right? So it's the moon that is so far away, feels the gravity of the Earth, and is orbiting around the Earth because it feels the pull to the Earth. The astronauts in the International Space Stations flying around the Earth here, they also feel the gravity of the Earth for sure. So why do they look like they are weightless, right? That they are floating in space and all. That is because they are free falling. And it's the same sensation, and we'll talk a lot more about this, but it's the same sensation you have if you're jumping off a trampoline into the swimming pool. While in the air, jumping, you will not have a sensation of your weight. You feel weightless. If you were inside an elevator and if someone were to cut the cable of the elevator and you're free falling inside that elevator, everybody, everything would be floating and free falling down. You would feel like an astronaut, floating like an astronaut. If someone was recording, you would be floating like an astronaut. So that's the phenomenon of weightlessness. So weightlessness is not related to whether or not there is gravity, right? You stop feeling your weight, but there is gravity, right? We stop feeling our weight once we don't have anything to push against because everything is falling at the same rate. So we'll talk more about that, but you cannot have left the Earth's gravity until you're really, really, really far away from our planet, well beyond the moon. Okay. The North Star is the brightest in the sky. We hear so much about the North Star, etc. The North Star is a star number 50th brightest star in the night sky. So it's really not the brightest at all. And we'll see more about that. We'll go in the planetarium. You also had your first lab when you were exploring the Stellarium, that software that is freely available online called Stellarium. You already from that, Stellarium is very good. It gives you an idea of the brightness of stars, right? And Polaris is tiny in comparison to so many other stars. There are 5049 stars brighter than Polaris. Okay, so the North Star is called Polaris. And there are many more stars brighter than that. And you can look at outside and in the night sky and you will see that. So you don't need a degree. You don't need to have taken an astronomy class to realize that. So on a dark night, you see millions of stars. Really, do you? From Long Island, you go out and you see millions of stars. Maybe if you're in South Hold, if you go to the North Fork, if you're in Montauk, really far away from everybody, you're probably going to see thousands. Not millions, not millions. You see thousands. That's the limit of our eye. If you go to a really, really dark spot, a perfectly great observing spot, actually one of the best spots to observe around us is actually in Cherry Hill in Pennsylvania. You got to drive quite a lot. It's a protected sky place. There's really no surrounding lights of towns and cities all around. So you really see thousands of stars, but not millions. For millions, you will need a telescope. You need more than that. And in a city, if you're in New York City, boy, you're lucky if you see a handful of stars, right? So you need to be in a dark place as well, and you would only see a few thousand in the best of hypotheses with your naked eye, assuming this sentence is talking about the naked eye. Total solar eclipses are rare. Well, eclipses occur 2 to 5 times a year. Okay, so is that rare when something occurs 2 to 5 times a year? And in the case of solar eclipses, they occur 2 to 5 times a year, but you have to travel to different parts of the world to find them, right? Because the solar eclipse happens in a tiny little strip of the sky. So you got to travel around the world to find these events 2 to 5 times a year. If it is a lunar eclipse that also occurs 2 to 5 times a year, you just sit down and wait. It will happen 2 to 5 times a year, wherever you are. But the solar eclipse, you do have to travel. If you're sitting down in one place and wait, I want to see a total solar eclipse here again, that will take about 100 years. So if you're sitting down in one spot, you don't want to travel around hunting for solar eclipses that do happen 2 to 5 times a year, then it will take you about 100 years for it to happen right above your head again. Okay, so that's the rate. Then it would look rare. But in general, eclipses are not rare things. They occur 2 to 5 times a year. Okay, the solar one, you get to travel. The lunar one, it happens 2 to 5 times wherever you are. Days get long in the summer and short in winter. So, what was the shortest day of the year? This is something you know from school. The shortest day of the year was like December 21st, right? This year was, I think, December 21st, right? And when is the longest day of the year? We normally say June 20th, 21st, 22nd. It varies a little bit what's the date, right? So that's the longest day of the year. Then is the start of the summer. And December 21st was the shortest day of the year and is the start of the winter. So if December 21st was the shortest day of the year, what happens with December 22nd, 23rd, 24th, 25th? They are longer than the shortest day of the year, right? So in the winter, so when the winter actually starts, days are getting longer. So cheer up, people. Days are getting longer. We are in the winter, but days are getting longer every day. There's more sunlight every day. So that is a thing to look forward to, right? Especially now in the winter. So the sentence is not quite right. Days, uh, they don't get long in the summer. They actually get shorter after the official start of the summer. And days get actually longer after the official start of the winter. Not shorter, but longer after the official start of the winter. At high noon, the sun's directly overhead. Well, even in the peak of the summer, go out here in latitude 40 degrees in New York, in Long Island, go and look up. Even in the middle of the day, you're never going to see the sun right above your head. That's because we're too far north. We're not in the equator. We're not inside the tropics. The sun is never going to be right above our head. Never. And that's something you could have observed. You're never going to have a shadow that is perfectly just right under you. It's always going to be tilted. And that has to do with the fact that we live too far north from the tropics or the equator. The sun rises in the east and sets in the west. Well, you are now in an astronomy class, so we're going to need to be a lot more precise about that. You guys have used Stellarium, the software. You can go there and check, but the sun now in the winter is always actually rising south of east and setting south of west. So this is why we have less exposure to the sun, because is towards the south and we live in the north. The sun is more towards the south, we live in the north, so no wonder we have less sun now in the winter. So we're going to be more precise with that. East is a cardinal. East and west are specific points in the horizon. And if you're shifted from that point, we're going to say, oh, it's south of east. Oh, it's south of west. Or it's north of east. It's north of west. Okay. And Stellarium can show you that. So no, the sun does not rises always in the east and sets always in the west. That actually happens only twice a year during the equinox. So March 21st, September 21st, that's going to happen. But all the other times of the year, that's not right. The sun is always shifted a little bit east, north, or a little bit south of east or west. And we're going to need to be precise with that. The moon comes out only at night. No, if you can see this, the clear skies any of these days, this is a week of bad weather, right? But if you can see the clear skies this week, you see the moon is in a first quarter phase. So what it means is that the moon is going to rise at around noon and the moon's going to set around midnight. So you will see the moon in the middle of the afternoon. You can see the moon in the middle of the afternoon this week. And yep, so the moon is not up only at night, right? So here we go. I have this little stellarium view here for you guys. And this is today. Okay, so this is the day today. I'm recording this on the 26th on a Monday. That's the sun. Here as you see west. This you see south. So you see as we play this, the sun is really setting. Look at that. The sun tonight is really going to set what? South of west. Is that west? No, is that south of west? Look at the sun. The sun, the word sun there. The sun is south of west. It's not on the west. To be on the west, you would be setting right where it says W there. Yeah, and it will shift over the days. As we are here in Stellarium, we can already go and scroll down a little bit. Ah, look at our moon, see? So that's exactly, if there were clear skies, you would see the moon, and this is what? This would be about 2 in the afternoon, 3, etc. Yeah, the moon is also up during the day. Okay, so what's the moral of the story of all the sentences that I was showing to you? You don't need a degree, you don't need to take a class, you need to be observant. So we can do that better just by being observant. As a science, and that's the nature of science. And as an astronomy student, we ask you to be observant of nature and the universe around you. That will already help a lot and is a good lesson for life. Be curious and cultivate asking why and how. Think critically. That's what it is to, instead of repeating a sentence and believing on it, think critically. Think about, but I've seen this differently. Hold on. Let me search for some explanations. Think critically by searching for different facts, avoiding biases or preference of opinions. Okay. Concentrate on learning rather than believing, right? And we are eternal students in life. Einstein used to say that education is not the learning of facts, but the training of the mind to think. And that's a lifelong endeavor. All right, so let's talk about what is our place in the universe, how we came to be, how the universe came to be. The universe was, as we know, as far as we know, created, the universe that we know was created 13.8 billion years ago. That's the time that all the research has converged on 13.8 billion years ago. And what is our place in this universe, right? How significant are we? What is our size in respect to the whole thing? And how many Earth's planets are there? So one of the first ways for us to put everything into perspective is to look at this cosmic calendar. So in this cosmic calendar, we are going to compress the whole history of the universe in 12 months. So it's 13.8 billion years that we're going to compress in 12 months. So every month is like a 1.1 billion year. Okay, so our universe was born on January 1st, and January 1st was then the Big Bang. The Big Bang is this sudden expansion of a singularity, of a point of, it's not even a point, it's the beginning of space and time. And that expanded all of a sudden. So we don't, it's not really an explosion, it's just a sudden expansion, right? And we call that the Big Bang. And it occurred 13.8 billion years ago. What was there before? That's the field of cosmology, and that's the field where that's part of cosmology. But in a part of cosmology that we, as far as we understand, there's no way to prove other hypotheses, whether there were multiverses and things like that. But our universe, the space and time that we live on, expanded 13.8 billion years ago. So it's not like there was another space where our space expanded on, because we cannot see any other space beyond our space and time that is our universe. So our universe, our space and time, all that we can measure, all that we are, expanded and was created 13.8 billion years ago. We cannot measure anything beyond that, as far as we know so far. So that was January 1st. Around now with James Webb Space Telescope, we're discovering that the first galaxies were formed much earlier than we think, in around 300 million years or 500 million years after the formation of the universe. We already had, after the beginning of the universe, the Big Bang, we already had the first galaxies. So it's really about the second, third week of January already, we'll have the first galaxies. And that has been a revolution from our thinking just with the findings of James Webb Space Telescope in the past 5 years or so. So that's pretty amazing. So here we go. So about the second or third week of January, the first galaxies were forming. Our Milky Way galaxy, we measured the age of stars in our Milky Way galaxy. We see some of them. The oldest stars in our galaxy are 13 billion years old. So our Milky Way galaxy, let's say end of January, early February, that's when it was forming. Okay, so that's our Milky Way galaxy. Um, and then the first stars, galaxy is an island of stars. So that's when the first stars were also born, and the galaxy is this ensemble of these first stars. The first massive stars, more the most massive ones, died first. They died, they were forming new elements inside, and then they ejected all the material new elements to space. And now this ejected, these gases, these new elements, then are going to be reused, collapse again to form a new generation of stars. So when our galaxy was formed, there was the first generation formed with the first generation of stars, which died quite soon after the first big ones, the first stars, the first big stars. And let's say around April, the second generation of stars were forming out of the leftovers and the gas of the first generation of stars. Okay. Now, the second generation of stars also will have a life, and eventually by maybe July, will die and will eject the massive ones because they're the ones that have the shortest life. Will eject a lot of their mass out, a lot of gas, more new elements that were formed. And then all the material then again be used to form the third generation of stars. And here we are in September. Here we are in September when we form our sun in our solar system. Our sun is a third generation star. Our sun had a mother, a father, and a grandmother and a grandfather since the formation of the universe. So our sun is a third generation star, and we'll talk more about that when we get to our sun. But soon after our sun was formed, the planets were formed around it. So around September, so that's when, right, the universe about 9 billion years old or so, and our solar system was forming, and that's here early September. For about a billion years to maybe less than a billion years, the first signs of life came up on Earth. Okay, so that's here marked as late September. So it wasn't that far from the formation of the Earth, right? Maybe half a billion years to 1 billion year. The first signs of life, we have the first fossils and signs of life on our planet, on Earth. So that's here at the end of September. Now, that was unicellular life, the simplest type of life. So only by December 17, now in this cosmic calendar, that multicellular life then popped up. How did it pop up? You can study the search for life in the universe and the beginnings and the ingredients for life. That's a course we offer here at Suffolk. The biology course is about the deal with evolution and the history of life. But this was the time when our planet had more oxygen than carbon dioxide and other gases in the atmosphere. Plants have been slowly producing enough oxygen. And so there was an event of mass extinction before because this oxygen was very all of a sudden poisonous to everything that existed before. A lot of things happen anyway, but this Cambrian explosion happened around December 17, when probably there was an ozone layer protecting everything on Earth from ozone layer from the oxygen. A lot of the oxygen produced the ozone layer protecting the Earth from a lot of the harmful ultraviolet light. Uh, right? So that could be some of the reasons why all of a sudden, this is a topic of research and study, from unicellular life, we've been waiting for 3.5 billion years with just this unicellular simple life, then poof, Cambrian explosion, multicellular life that we need to develop complex life like ours, that came up. The dinosaurs came up on December 26 and they were extinct. We know there were about 4 or 5 extinction events. Go to a museum, Natural History Museum, you're going to see those extinction events. Several of them happened. We know dinosaurs were extinct in this cosmic calendar around December 30th from a giant asteroid that crashed around the region where Yucatan Peninsula in Mexico is nowadays. We know that very well now. But that was the extinction of the dinosaurs. And actually, the human beings that we come from only showed up in this cosmic calendar at 9 p.m. of December 31st, the last hours of December 31st. The modern civilization only came up in the last seconds of December 31st. So that is where we are in this perspective of the cosmic calendar and how long it has been our experience in respect to the age of the universe. Only a few seconds in respect to uh, the whole year in this cosmic calendar. So what is this universe we've been talking about? Is the sum of all the matter and energy that exists. So it's not just stars and galaxies, it's also the gas. There's a lot of gas in between stars and galaxies, but it's asteroids, it's planets, it's comets, it's dust. But what else? We will learn that, especially if you take Astronomy 102 in the future. Say, if you like, Astronomy 102 is astronomy about stars and galaxies, and we talk more about the beginnings of the universe. We know our universe is composed mostly of dark energy. So it's energy. And then there's another component of our universe that is 5 times more than the things we can see. That's called dark matter. So dark energy, dark matter, all of these are components of our universe beyond the only 5% that we can see and know about and study so much. We study galaxies, stars, gases, dust, right? Comets, planets, and yeah, well, that's only 5% of our universe. 95% of it is dark energy, another thing called dark matter that we are actively studying to figure out what they are. But our universe is all of that together. What is a galaxy? It's a great island of stars in space, all held together by gravity and orbiting a common center. We think that all the major galaxies in the universe have a supermassive black hole in them. There are many different shapes of galaxies. If you study Astronomy 102, we go over that. Our Milky Way galaxy, we can never take a picture of our own Milky Way galaxy, so this is an artistic view, right? But we know it's a spiral galaxy, it has arms. Ooh, the sun is right here, about almost halfway from the center is 28,000 light years from the center of our galaxy in one of the arms. That's where our solar system is. And when we talk about galaxies, we measure everything in this scale called light years. So although the word years is here in this unit, a light year is actually a distance. It's not a time, it's a distance. It's the distance that it takes light to travel at the speed of light for a year. So 1 light year, if you want to know in miles, is like 6 times 10 to the 12 miles, if I round it here. Okay, 6 with 12 zeros miles. So our Milky Way galaxy has a diameter of 160,000 light years. Even if we could travel at the speed of light, and we cannot, is one of the limits in our universe. If we could travel at the speed of light, it would take 160,000 years to cross our galaxy. So it's not something feasible by humans, okay? And we will never get to the technology of traveling at the speed of light because that's one of the limitations of our universe. And we'll have a class being offered here in our campus very soon, not this semester, probably maybe next semester already. That's called Astronomy in the Movies and TV. And we go over now the possibility of doing this space travel with wormholes and hyperspace and all these other ways and warp drive and all these other ways that are talked about in science fiction. And so take that class if we're to go over more about this. But we can never, nothing that has mass can travel at the speed of light. Only light can travel at the speed of light. Anyway, it would take 160,000 years to do this whole thing, to cross our galaxy. So from the center of our galaxy to the sun, it's about 28,000 light years. So if light takes 28,000 years to travel from the center of our galaxy to our sun, 28,000 years. So in between the planets, the stars, and all, there's a lot of gas. It's a lot of gas in a galaxy, right? And this gas can come from places where stars died. So the four pictures here at the corners are actually the two top ones are the end of a massive star. So this was ends of supernova. These were supernova explosions, and this is the leftover bubble of a supernova explosion. The bottom two ones is what's going to happen to our sun. They're called planetary nebulas. The sun doesn't, it's not going to explode as violently as a supernova because it's a low mass star. It's just going to poof out its outer layers. And it's very pretty. It's called planetary nebula. But anyway, the four pictures in the corners are gases from the death of stars. And the two pictures in the middle are gases that are then forming new stars. These are the birthplaces of stars. This is the Orion Nebula. This is another region, the Eagle Nebula, close to the Orion Nebula. This is a birthplace of stars. So when you see another nebula, it may be the death place of stars, maybe the birthplace of stars. So here's a little video just to put things in perspective. What you have here drawn here is the Orion constellation, the Hunter, right? Do you remember the three stars? That's one of the constellations people know the most. The three stars in the belt of Orion, the Hunter, his shoulders, and yeah. Sometimes I can make a little drawing here. But this little movie is inside of our galaxy. So we started in our galaxy, our Milky Way galaxy, the or constellation of Orion is in our Milky Way galaxy, stars in the Milky Way galaxy. Here in the middle is the Orion Nebula. Inside of our galaxy, what you see here is the main disk of our galaxy here, okay, the Milky Way. And notice how the stars, even the stars in the belt, how we think that they are so so close together, but it's a projection effect, right? They are actually, look at that. I'll stop here. These were the three stars of the belt. Look at some of them are much closer to us, some of them are much further away. So constellations are always a projection effect. The stars don't necessarily are next to each other, and we always have to remember that, right? So we are traveling to the Orion Nebula, which is in the constellation of Orion, and is the birthplace of stars. Our sun was born in a nursery like that in the past. This is so-called close, also part of the Great Orion Nebula, the Horsehead Nebula, also birthplace of stars. We're going to another birthplace of stars. We are all inside of our galaxy still. This is called the Rosette Nebula. It's again another nursery. New stars are formed from all these gases here, and you see it shining bright because it's new stars. They're shining so bright, illuminating all the gas. And here we go now to the Crab Nebula. That is now gas left over from the death of one single star. And so that's the Crab Nebula, and was a star that exploded, and that's all that is left over here. Okay, so it's the Crab Nebula. There's a pulsar in the middle. Boom, 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 boom. Is what's left over from the death of that type of stars. And we cover more of that in Astronomy 102, actually. Oh, so we are leaving now the plane of our Milky Way galaxy. Look at that. So we're zooming out, leaving the plane of our Milky Way galaxy. Our Milky Way galaxy is in a group of local galaxies. There are three big ones. Our Milky Way galaxy is sort of the second largest one. Andromeda is actually the biggest. So we're going to see the two other companions that are pretty large. There's a lot of little satellite galaxies around our galaxy. They're really dwarf, small ones. This is Andromeda. This is Andromeda, and this is the Triangulum Galaxy, or M33. Those are the three big ones then. Milky Way, Andromeda, and M33. This is, we're just going through this is star formation region on this other galaxy called M33. And now we're going to zoom out. We're going to zoom out, and all that you see, every little dot, every little piece of light that you see in this picture is a galaxy. Everything's a galaxy. It's an island. We're zooming out. Everything's a galaxy here. It's not a star. And you see how stars, galaxies are aligned in filaments. That's the large scale structure of our universe. They're aligned in filaments. And there are nodes, clusters, right? Big, giant clusters in knots of these filaments, where you have an accumulation of lots of galaxies. And so this one is called the Virgo Great Attractor. Our galaxy and our local group of galaxies moving toward that. Very slowly, but there you go. Well, fast, but it's not going to crash anytime soon. You don't need to worry. And at the center of this giant superclusters, you always going to have a massive elliptical galaxy. That's this one here, with some of the largest supermassive black holes in the universe in the center. There we go. So that's just to give you an idea, a taste of our universe. What about our solar system? So when we talk about our solar system now, we're going to just talk, it's not just the sun, it's not just the planets, right? There's more to our solar system. But when we're talking about our solar system, we switch scales. Instead of referring so much about light years, right? Light years is what we use for galaxies and outside of our galaxy and so on. We're going to talk about astronomical unit. So what is an astronomical unit? It's the distance. We define the distance between the sun and the earth. So that we're going to call 1 AU, one astronomical unit. If you want to know the number, 150 million kilometers, okay? Or 90 million miles. 90 million miles. There you go. That's one astronomical unit. It's less than the light year, of course, a shorter distance than a light year. It's officially the distance, the average distance between the Earth and the Sun. So here's the Earth, here 1 AU, one astronomical unit from the Sun. Jupiter's 5.2 astronomical units from the Sun. Saturn 9.6 astronomical units from the Sun. Neptune, the last major planet in our solar system, is 30 astronomical units from the sun. But now our solar system is not just this. Our solar system, there's an asteroid belt. The asteroid belt is in between Mars and Jupiter. So, and millions of billions of asteroids there. They're small, but there you go. That's part of our solar system. Now, beyond Neptune, there's another belt of icy bodies or possible comets. Okay, the asteroids are more rocky things, whereas the icy bodies in the Kuiper belt, they're more comet-like. They have more ices and less rock and more ice. And that's this donut-shaped belt of leftover icy bodies left over from the formation of our universe that's called the Kuiper belt beyond Neptune. These are components of our solar system. And zooming out even further, now we need to zoom out a lot to almost a light year away from the sun. We get the very last component of our solar system that's called the Oort cloud, which has also comets and icy bodies that were the very final formation of our solar system. So the Oort cloud is spherical all around our sun, whereas the asteroid belt is a belt, and the Kuiper belt is more a donut-shaped belt. But the Oort cloud, the very final last thing, which is about almost 1.1, 1.5 light years from the sun, that's the last component of our solar system. That's the leftover from the formation of our solar system. So these are all components of our solar system. It's not just the planets, right? Oops. So it's not just our planets. And how special is our solar system? Well, we detected, found, and measured, and tested and proved that made specific measurements of over 4,000 other solar systems. Okay, and out of these 4,000 other solar systems, we found in them another 6,000 planets in these other 4,000 solar systems. Okay. Now, and this number keeps increasing. This is from the NASA Exoplanet Archive. This number will keep increasing. We believe that for every star, there is statistically, there is a planet associated with it. Not all stars will have planets, but statistically, it's as if every star has a planet. And so how many stars we have in a galaxy like ours? 100 billion stars. How many planets we're going to have in a galaxy like ours? 100 billion planets. So these are the ones it takes time. We've tested, we took spectra, found ways to measure if sometimes their atmosphere. So we have data about them. This number keeps increasing as we keep finding data. So we expect to have the same number of planets as we have stars in our galaxy. So stars, what is a star? Our sun is the closest star to us. What is this? A star is the difference between a star and a planet or anything else is that a star will be massive enough that will do nuclear fusion in its core. So nuclear fusion is when you fuse two atoms and produce a heavier one. And when you do that, this combination of two lighter atoms, two lighter nuclei into a heavier one, releases a lot of energy. And so you need to be massive enough to have those conditions, the temperature and density inside to do nuclear fusion. So that's a star. Then it's anything that is doing nuclear fusion. And you have to have a minimum mass to start doing nuclear fusion there. And so we have our sun here in this picture is in the visible band. So again, the sun is a white star. If you take any picture of the sun in outer space, especially without the effects of our atmosphere scattering and etc., the sun is white. Um, uh, so when you see pictures, you're going to see so many pictures of the sun and of the stars in different colors. Watch out because we put pictures, sometimes fake colors in images, right? To enhance contrast and all. So this is an image taken probably in age. Oh, this is ultraviolet. In ultraviolet, the ultraviolet light does not have color. Okay, can you see ultraviolet? No, you cannot see ultraviolet. So ultraviolet doesn't have colors, but we put a fake color here. So watch out in astronomy when you see colors. Oh, this is a color. The color of the sun with our eyes is white. So this is a fake color in ultraviolet because ultraviolet doesn't have colors. So the source of energy in the solar system is entirely coming is coming from our sun, right? There is very little coming out from the interior of our own planets, but by far the energy of our solar system is the sun. 100 times wider than the sun, 300,000 times as massive than the Earth. Sorry, 100 times wider than the Earth, 300,000 times as massive as the Earth. The sun is about 5 billion years old. And our models of evolution say that it has another 5 billion years ahead of it, but within another 500 million years, we should leave because the sun is slowly getting bigger in a matter of millions of years, slowly getting um, hotter in a matter of millions of years. This has nothing to do with any kind of climate change in our planet. All the scale of astronomical changes take millions of years. So in millions, in 500 million years, the sun will have gotten 5% hotter than it is nowadays. That is already going to cause a big trouble for life on Earth. So we have 8 planets, 8 major planets in our solar system, right? And a planet then is something that orbits is an object that will orbit a star and will have clear, it will be round. It has enough mass to be round, not potato shaped. That will be then an asteroid or a comet or something else. And it will have cleared its surroundings from anything that looks like it. So it's not going to be an asteroid or it's not going to be a dwarf planet because an asteroid and a dwarf planet have a lot of other things that look like it around it. Haven't cleared the orbit of a lot of other debris that look around it. So this is the official definition of what is a planet. Now, then, yeah, a few years ago, since until 2006, Pluto was our 9th planet, but it has been demoted in 2006 to dwarf planet. There are 5 total dwarf planets, as far as in the number will probably increase. Ceres is the largest asteroid in the asteroid belt. It is massive enough to be round. So could round, it's one of the prerequisites to be a planet. But it hasn't cleared its surroundings from objects like it. Ceres is embedded in the middle of the asteroid belt, full of all the asteroids that look like it. So that doesn't make it a planet. It makes it a dwarf planet. Same thing about Pluto. Pluto was demoted in 2006 because we started finding so many other things around the Kuiper belt, around where Pluto is, that look like Pluto. So Pluto was demoted too because there's a lot of neighbors around it that look like it. So it's a dwarf planet now. We'll talk more about these things as we move on in the semester for sure. This is an overview class. So, of course, part of the solar system, the moons, the satellites of the planets are a very important part of our solar system. Actually, they are a lot more interesting than the planets themselves sometimes. Yes. So Jupiter, all the Jovian planets, the gaseous planets, because they are much more massive than the terrestrial planets, they have a lot more moons. And these moons are very interesting. We are sending probes to find possibility of life in the solar system to one of the moons of Jupiter called Europa. So Jupiter about 95 moons, Saturn 274 and growing. I had to change this number just last year, 29 moons, Uranus, Neptune 16, and so on. Asteroids, then, this potato-shaped building blocks of our solar system, our planets were formed from lots of these planetesimals that were the asteroids, and comets, which are the counterparts to asteroids, but they have more ice than rock in them. So our place in our solar system, this is a picture taken by the spacecraft Cassini. This is Saturn, as you're seeing here. The sun is behind Saturn. And so this pale blue dot circled here in red is our planet Earth. So it is a fantastic perspective of how tiny we are in comparison to the scales of what we are studying this semester, right? Physically tiny. Finally, I wanted to end this overview of astronomy lecture highlighting that you are 99% of your human body is made of these elements: hydrogen, oxygen. Hydrogen and oxygen make water, H2O. You're mostly water, right? But you have a lot of carbon inside of you, nitrogen, phosphorus, and calcium. Everything is circled here in pink. So the bug bang, I have to correct the slide. Um, so 99% is this thing circled here. Everything in the periodic table, guys, except for some of the elements that were produced artificially in laboratory here at the bottom, okay, human made, all the other ones were made by stars, were made in astronomical events. So carbon and nitrogen comes from dying low mass stars like our sun. Our sun will release a lot of carbon and nitrogen that then will be material to form new stars and new planets and new life. Look at the hydrogen. The hydrogen came from the Big Bang, from the formation of the universe. The oxygen, the phosphorus, came from dying high mass stars, supernova explosions. Calcium came from white dwarf supernova as well, a specific type of binary supernova. So you are stardust. We have this table of the elements with their astronomical origins in the back of the astronomy room, always for you to look at in our room 201. So I hope you enjoyed this short overview of our uh, astronomy and our universe. And I'll see you in class soon. Take care. Bye-bye.